Hello, and welcome to what's going to be my very first physics lab. Today we're going to be talking about motion at a constant velocity. I'm going to be comparing the position versus time graphs of both an experimental position that we recorded on tracker and a modeled position based on a constant velocity calculated using Newton's second law. So Newton's second law states that the final velocity is equal to the initial velocity plus net force divided by mass times the change in time. So if velocity is constant, then velocity final has to equal velocity initial, and therefore F net over m times delta t has to equal 0. If this is all true, then the final position is equal to that initial position plus the velocity times delta t. So in order for this to work, we have to make a few assumptions. So first we have to assume that net force is all equal to 0. There's going to be forces coming at it from all different directions, and it's important to assume that that net force is 0 because, as stated before, if that force is not 0, then there is no possible way for velocity final to equal velocity initial, and therefore velocity isn't constant, it is changing. We also had to assume the ground was flat. For obvious reasons, I'm doing this in a North Ave apartment, and the ground is most definitely not quite flat. We also had to assume that the velocity recorded by tracker was indeed the correct velocity. Tracker could easily not be able to trace things simply because the video quality is not stellar. We also had to assume that the spot chosen on tracker is the actual start position. As you can see in my tracker model here, start position I chose is right here. That could or could not be inaccurate based on where we're starting, and my model has accounted for some of that error. So as you can see, tracker is tracking this as it moves through space across the x-axis here that I've set up, and as you can see, it continues to print out data that we'll be using to make our model here. Alrighty. So next what we're going to do is we're going to take this data and we are going to use it to make a few assumptions, or we're going to use it for average velocity. So to calculate this average velocity, I decided to do 2 points and compare them. So we have the first track time and position as well as the final time and final position. So the initial velocity ended up coming out to be this, as we had used the initial position to adjust for the slight error that I may have had. Initial velocity ends up being 1.06, as well as 1.05 for the final velocity, and the average here together is 1.055. So this is the average velocity that we're going to be using to set up our model. So here in our program, as you can see, I took it and I changed a few things. I changed 1.055 to be our velocity. I changed delta t to be 1 over 30 since our tracker was recording things in increments of 1/30th of a second. And then I changed the upper bound time to be 2.835. So we run this program. As you can see, we get, it stops right before it gets to 3 meters, which is exactly the distance that we covered in the tracker. So now if we go back, we can clearly see that, excuse me, we can clearly see that the data here all lines up, and as you can see, the blue line being the predicted versus the red line being the actual recorded data, they are similar. However, they split off a little bit towards the end, likely due to some error with the tracking, or like I said, the unevenness of the floor. So there's tons of forces that are going to be acting on the object as it moves, and it's only constant if the velocity is only constant if all those forces all negate each other. And so air resistance is a force that's acting on it, friction is acting on it, the force of gravity is acting on it, and also the weight is acting on it. And the weight would be negligible if it were perfect constant motion, but like as I said, the floor is uneven, which means that its weight comes into play as a factor. And that could have been part of the reason that the results were not perfect. So it's impossible to really track all of these forces that are here, and I think that's an important thing to an important distinction to make. Then finally, what we have is we have to ponder a what if question. So what if all of our x values, what if the axis was flipped, and what if all x values were negative x values? So if we were to flip the axis here on its head entirely, what you would end up getting is, instead of a constant velocity moving in a positive direction, you would still have a constant velocity magnitude. You would still have a constant magnitude. However, that velocity would be going in the negative direction instead. So the magnitude would be unchanged, but the direction would be very changed. All right, thank you.